In this module, you're going to learn about tuples. But before we can talk about tuples, we need a problem to work on. For this reason, I will first go through a problem, a TSP problem, and a model that solves it without the use of tuples. The N indicates how many cities we are to visit. A TSP problem is a problem where you are a traveling salesman, you have a number of cities given, and you have to visit them all and return to where you came from. You want, of course, to do this traveling as short a distance as possible. So, lowercase n is the number of cities, the range n is the range of all the cities, and we have a distance matrix. In this case, a 5 by 5 matrix. As you can see, the distance matrix has some data that seems a little bit weird initially. There are zeros, that's a zero distance. In this case, that's from city 1 to city 1. And there are distances of up to 1,000 here. And in this case, that should be interpreted as you cannot travel directly between these two cities. The decision variable x here, we have 1 for each entry in the distance matrix, indicating whether that distance is actually used. It can also be interpreted, am I going from this city to this city? There is also a secondary decision variable that is used for sub-to elimination. What that means, I'll get into in a little bit. The objective function is of course a minimization, and what we're minimizing is the distances that we're actually using. There are a number of constraints that we need to enforce. First, it's not allowed to take an edge to yourself. So the next city you visit cannot be the city you're currently in. So note that the i's here are the same. So you cannot go from I to I. The next one, we take I and j from n. And we're only going to look at the cases where the distance from I to j is more than 1,000. These we're going to say you can't visit those. You cannot use that edge. The next constraint you'll see is a flow conservation constraint. So we go through all nodes and we sum up all of the edges out of it. That is how many times we leave the city. And we sum all the edges going into the city, that is how many times we go to the city, and these of course should be equal. Each time we enter a city, we must also leave it again. Then we have a coverage constraint, and that simply says that we must go into each city, that is we must visit each and every city. The next constraint is a sub-to elimination constraint. Its basic job is to prevent you from creating too small tours that end up where they started, but otherwise do not meet. If you want to know how it works, I suggest you take a look at the transcript to this video. So why are we not satisfied with this model? It has a number of problems, though it's not the worst case you can come up with. The first problem is if we scroll up and take a look at the distance matrix. We have a lot of entries there that we are not actually planning on using. We have the 0 length entries, we have the 1,000 length entries. To actually prevent ourselves from using them, we have to have 2 additional constraints that enforce this. If we screw up a little bit in this, we'll have errors, that is, we are more prone to errors. We have more constraints than we strictly need. And we also have some decision variables that we are forced to never use. That is, we also have too many decision variables. So we are also introducing a lot of overhead into our model. So what can we do to actually fix these problems? Well, the problem stemmed from having entries in the distance matrix that we were not actually planning to use. So what if we could instead create an enumeration of the edges that we were allowed to use, and then just use the decision variables to determine which of these we were actually going to use? This, of course, demands that we are capable of expressing what we need to know about edges in a convenient manner. And for that, we're going to use the tuples. What I've inserted here is a tuple. It has the name arc, that's one I chose, and whatever is within those brackets is something that an arc contains. In this case, there's 3 values. There's an int, a from node, there's an int to node, and there's a float, a distance. So this is a template that specifies what goes into an arc, and that's where does the arc originate, where is it going, and what is its distance. What we need now is to specify what arcs we actually are to use, and this is done like this. And let's go through it step by step. You have seen this kind of notation before, but with strings instead of arcs. This is just a set of arcs, and this is the name of the set, in this case arcs. On the right side of the equality, you see what we initialized that set to. Again, this is just a list, and it contains some elements, this being one of them. The interpretation of this element is that it's an arc, that's specified over here, and the first number indicates the from node, so this is from node 1, then the to node, that's to node 4, and the distance is 4. This list is actually a direct translation of the previous distance matrix. The translation was in practice done using an execute environment. But this is a valid way of actually entering the data into the model. What we need to do now is we need to have some decision variables. We still need a range from the last model, but we need some decision variables. So dvar for decision variable. We again need a boolean. Let's call it x again, like usual. But in this case, we need one for each of the arcs. We are also going to use the sub-to elimination constraint from the previous model. Then we need the objective function. We need to minimize. And now we're going to use this set of arcs. So we need a sum. We need it for a in arcs. So a will be an arc in this case. And what we need to do is we need to take the distance. This dist refers to that dist up there. And we need to multiply it with whether we actually use that arc. Then we need the constraints, of course. Subject to. And what we initially need to do is have flow conservation enforced. The flow conservation constraint can be written like this. We need a constraint for all of the nodes that we are going to work with in this model. Okay. And then what do we need? Well, we need the sum of all selected arcs going into the node to be equal to the sum of all selected arcs exiting the node. This is done using a sum. Again, a in arcs. So a will be an arc, but we're only interested in everything going into the node. So we want the a in arcs where the following holds true. A dot the to node equals I. Okay, and of course we are only going to sum those that we have actually chosen, and this should be equal to all of the arcs going out. So sum a in arcs, but we're not interested in all the arcs, but only those where we're going out of the node that we're currently looking at. And of course, again, we are only summing over those that we're actually selecting. So this is how the flow conservation will look in this tuple formulation. Next thing we need to do is enter a coverage constraint here. So how are we going to do that? Again, we're going to make a coverage constraint for each of the nodes. And what we're going to do, we're going to sum up all the edges that go into that node. So all the arcs, but only where we're actually going into the node. And what should that equal? Well, we should select one and only one of them. Lastly, we'll need a subto elimination constraint, and that will look like this. And if you want to know how to interpret it, we are going for all the arcs. We're going to enforce something. We are going to say that if the arc starts with or ends with the first node, we're going to ignore it. If it doesn't though, we have to set this u value, and this u value +1 must be less than the u value where we came from if we have the edge selected. If we do not have the edge selected, this will be 0, this will be 1, the whole parenthesis will be 1, and we'll times 1000, and this whole constraint is trivially fulfilled. This is the entire TSP formulation. No more constraints are necessary. If we go back and look, you can see we saved the 2 constraints involved in disallowing the use of specific entries in a distance matrix. We are not that error prone anymore, and we have successfully associated the data where we come from, where we go, and what the distance is for each arc. For some models, you can associate even more data. Also note that the reduced number of decision variables we have and the reduced number of constraints that we need to impose will make the model easier to solve in general. For those that might be a bit confused on how tuples work, I will now do a little recap. If you don't feel you need it, you may skip out now. So to recap the idea of tuples. The idea of tuples is to take some data and associate with each other so that they always go together. In this case, we create a tuple called an arc. And an arc consists of 3 different things. An integer that is from node, an integer that is the to node, the node we're going to, and a float that is the distance between the two. An arc can be initialized using this notation. 1 will be assigned to the from node, 4 will be assigned to the to node, and this 4 will be assigned to the distance. As with ints and strings, these tuples can be put into sets, for instance. It's basically a type you have defined yourselves. When the tuple is in a set, what we can do is, for instance, sum over it. So what we do here is sum over A in arcs. That means A is extracted from the arc set. We cannot use A for something other than to index, for instance, this decision variable directly, but if we want to access, for instance, the distance associated with A, what we use is the dot and then the dist name up here. You can see OPL also shows us what we're doing. In the first constraint, we introduce the flow conservation constraints. What we do is we have 1 for each node. Well, again, we sum over all the arcs, except we're only interested in those where the to node value in the arc equals the node that we're actually looking at. That is, we sum over the arcs going to that node. And what we sum is simply the decision variables, the x's, that tells us whether we selected that arc. So this sum will be the number of arcs selected that also go into the node. The sum on the other side of the equality is exactly the same, except that we are taking from node from the arc, and that means that we are summing over all the edges going out of the node. For the coverage constraint, again, one for each node, we sum over all the arcs, but we're only interested in those going into the node, so we sum over all arcs for which the following holds true. The subfield in the arc to node is equal to the node we're actually going to visit. And we sum over the decision variable as to whether the arc is actually selected, and the sums should equal 1. So we have to select exactly one arc going into each and every node. So this concludes the explanation of the TSP model. You can find it in the transcript and play around with it if you want.